Alright, so this video is basically going to demonstrate my knowledge and understanding of circular motion. The first part of the video will consist of a short demonstration of my understanding of the major concepts, just like we did for the Isle cycle in Unit 1. So first off, the definition of circular motion is the movement of an object along the circumference of a circle, or the rotation along a circular path. This can be uniform with constant angular motion, or constant angular rate of rotation and constant speed, or it can be non-uniform with changing rate of rotation. Along with this, there are also three main points of uniform circular motion that I'd like to mention. The first point being the direction of vector is not constant. The second point being the change in direction means acceleration. And the last point, speed or magnitude of the velocity vector is constant. So along with this knowledge and a few other formulas that I'm going to mention, we can approach number 12 now. So to begin, number 12 gives us the radius. Actually, I'm going to read the problem first, okay? So a 0.500 kg ball hangs from a 1.0 meters long string. The other end of the string is attached to a Newton force measuring scale. The string pulls up on the ball with a 9.8 Newton force, and the string and the ball in turn pull down on the scale with a 9.8 Newton force. The scale reads 9.8 newtons. Imagine that you pull the ball to the side and release it so that the ball swings like a pendulum at the end of the string. Predict the scale reading as the ball passes directly under the scale. Example, is tension greater than 9.8 newtons, equal to 9.8 newtons, or less than 9.8 newtons? Okay, so now that we read the problem, we can jump right into it. So first they give us the radius, which is equal to 1 meter in this problem. They also give us the mass of the ball, and that's going to get us 0.500 kilograms. Let me just change the size of this. And then after that, we can draw this diagram quickly. So with the pendulum and the ball, radius of this length right here, this length is 1 meter. We're going to make it swing this way. Doesn't really matter. It could swing left or right because it goes both ways eventually because of the forces. And the velocity is not equal to 0, and there is acceleration because the ball is swinging back and forth. And if we draw a force diagram right below it, you see that this is the ball. So this is the ball. Sorry for it being messy because it's kind of hard to write on paint. But this is mg, which is equal to 9.8 meters over second squared, as we learned in the last unit, to the last unit of dynamics. And along with this, we can jump right to this. Hold on. We can jump right to here of the formula that we learned in 2D mechanics, along with circular motion. The net force is equal to tension minus mg. And we also know that from this unit, it's also equal to m over velocity squared over the radius, which is greater than 0 in this problem. And from here we can draw an arrow down because this formula is derived from fc equals to m times velocity squared over r. And because of this, therefore, tension minus mg has to be greater than 0 because the velocity is not equal to 0 as the ball keeps swinging in acceleration motion. And because of this, we would think that the tension would immediately be 9.8. But because we have, okay, let me just draw an X. But because we have to do mass, mg, right? So it'd be the mass, which they gave us to us in the earlier parts of the problem, which is 0.500 kg times 9.8 meters over second squared That actually gets us 4.9 newtons. So this is our answer, except we know that t is greater than 4.9 because of the formulas above, and instead of taking 9.8 newtons directly, we have to multiply it by the mass, which is 0.500 kg, getting us the final answer that it has a tension of greater than 4.9 newtons. So that's my demonstration of the concepts of circular motion, along with the last unit of 2D mechanics, and as well as describing this problem.